Alright, so in this video, we're going to be talking about the difference between homotopic, enantiotopic, and diastereotopic. And this is important in your O-Chem II class, especially when you're talking about nuclear magnetic resonance spectroscopy, or NMR for short. Alright, so first we're going to be covering a brief definition of topicity, which states that some atoms or groups of atoms are going to present one NMR signal, while others present more than one. For the ones that present only one NMR signal, that means they're in chemically equivalent environments, and they show NMR peaks at the same chemical shift. But the groups of atoms or atoms that present more than one NMR signal are not in chemically equivalent environments, and as a result, they will display their peaks at different chemical shifts. Okay? Now, when you're looking at 13C NMR, a specific type of NMR spectroscopy, the number of signals corresponds directly to the number of different types of carbons. However, if you're looking at 1H NMR, which you should also be learning in an O-Chem II class, you also have to consider the protons, all right, or the 1H atoms. Are they in equivalent chemical environments, or are they in different chemical environments, okay? And finding this out in terms of whether they're homotopic, enantiotopic, or diastereotopic can help you figure out the structure of your organic compound, especially when you're looking at proton NMR, okay? Because in order to find out the final structure of your organic compound in question, you not only use 13C NMR and IR, but proton NMR is also pretty helpful. So if you can find out whether or not your two hydrogen atoms are homotopic, enantiotopic, or diastereotopic, that can help you deduce the structure of your organic compound, especially when you're looking at proton NMR. Okay? So homotopic. In this case, we're going to be looking at two hydrogen atoms because that's what you use for proton NMR. So two hydrogen atoms that are homotopic are in the same or equivalent chemical environment, and as a result, they display one NMR peak, okay? So they only display one NMR peak at the same chemical shift that is in units of parts per million, okay? However, two enantiotopic hydrogen atoms are equivalent but only in an achiral environment, but they still present only one NMR signal or one NMR peak. So what is achiral? Well, here's just a brief recap, most likely from O-Chem I, where you should have been exposed to this. So let's say you have your carbon atom in the center and it has four substituents, okay? So in the achiral case, you have at least two groups or at least two substituents that are the exact same thing. So for example, here we have four substituents. You have your chlorine, your methyl, and you have your two hydrogen atoms. These two hydrogen atoms are the same thing. So as a result, you have two substituents that are the exact same thing, right? But when you look at your chiral case, here you have your carbon atom in the center, you have four substituents, but these four substituents are all different. You have a hydrogen, a methyl group, a bromine, and a chlorine atom. There are four different things. So as a result, this center is chiral, while this center is achiral, because you have two substituents that are the exact same thing in the achiral case, all right? And finally, diastereotopic means that you have, so for example, when you're looking at two hydrogen atoms, if those two hydrogen atoms are diastereotopic, they are in different chemical environments, and as a result, they would present different NMR signals, okay? All right. So first of all, we're going to be talking about how to determine whether two atoms are homotopic, and in order to deduce this or to find this out, you can use the substitution test for homotopicity, all right? There are various other methods, more geometrical interpretations like the C1, C2 axis and all that, but this, in my opinion, the substitution test can be the most straightforward out of all the methods, okay? So let's say, for example, you have this organic compound here, and you have these two hydrogen atoms, and you want to know if these two protons or 1H atoms are homotopic. So what you do is you replace one proton with something else. For example, you can use a deuterium atom, which is also known as the 2H isotope, or it's also denoted as simply the capital letter D. You can use bromine, chlorine, methyl, whatever you want. In this case, we're going to do a replacement with the bromine atom. So you can replace this with bromine and you get this, or you can replace this with bromine and you get that. Okay, but you have to do both substitutions, not at the same time. You do one substitution at a time, and then you get these two compounds. So you have this one, and you have this one, okay? However, let's look at this one over here. So if you were to flip this compound just like that, flip it just like that, like you're flipping a burger or whatever you want to flip, you can see that once this molecule right here, this compound is flipped like that, bromine is going to be on top and hydrogen is going to be on the bottom, just like this molecule. So when you flip this molecule like that, you're going to find out that it's the exact same compound as this one, right? So as a result, these two protons are homotopic. So that's one case of using the substitution test for homotopicity, all right? So now let's go to the substitution test for enantiotopicity. So for two atoms or groups, in this case, we're going to be looking at two hydrogen atoms. Substituting one hydrogen atom with another compound should result in an R chiral center, while substituting the other atom or group, in this case, the other hydrogen atom, should result in an S chiral center, okay? Now, if you want to go over a review of R and S conventions, chiral centers, priority rules, there's a separate video called Chiral Centers and Priority Rules, also on my channel, if you want to check that out, okay? So, but before we get to the actual example, let's just go over a brief rundown. So, you have your original compound, all right? And like we said in around the beginning of this video, two enantiotopic hydrogens are equivalent in an achiral environment. So this environment is achiral because you have two different substituents. Well, you have two substituents that are the exact same thing. That's what I meant to say, okay? So your original compound starts as achiral, but when you do one substitution, you get one new compound that has a center that's chiral, and then when you do the second substitution, kind of like what we did here, that's how you do substitutions, you just replace. When you do the second substitution, you get a second new compound that also has a chiral center. And when you compare these two new compounds, they should be enantiomers, okay? So just to go into more specific, let's say we have this example over here, this compound. So this compound is achiral, right? Because it has two hydrogen atoms, two substituents that are the exact same thing, okay? So you start with an achiral original compound, and then you do the replacements, and you should end up with two compounds, both of which have chiral centers, okay? So you want to know if these two compounds are enantiotopic. So you're going to replace with something. In this case, let's replace it with a methyl group, all right? So we're going to replace this hydrogen atom with the methyl group here. You get this. And we're also going to replace this hydrogen atom with the methyl group here, and you get that, okay? And you have to do both substitutions in order for the substitution test to work, okay? So just as a brief recap, when you're trying to find out whether a center that's chiral is R or S, first of all, the lowest priority has number 4, highest priority has number 1, and you do it based off of atomic number. So hydrogen has the atomic number of 1, it's the lowest atomic number, so therefore it has the lowest priority of 4. Iodine has the highest atomic number, so therefore it has the highest priority of 1, okay? And then for chlorine and methyl, you can do similar comparisons. The dashed line means it's pointing into the board, and the dark wedged solid line means it's pointing out of the board, all right? So what do you do in this case? So you have both centers that are chiral, right? Because you have 4 different substituents, 4 different things. You've done your substitution. So now you have to find out, is it R or is it S, okay? So the way you determine this is, first of all, you take your thumb. I use my right hand because I am dominant in my right hand. You stick it in the direction of the atom of lowest priority. In most cases, it's going to be the hydrogen atom. So is the hydrogen atom pointing into or out of the board? In this case, it's pointing into the board because of the dashed line. So you stick your thumb right into the page, all right, into the board or into the page, and then you curl your fingers in the clockwise direction, because you can't curl your fingers in the counterclockwise direction if you're pointing into the board, right? So you curl your fingers this way, all right, in the natural method, and you find out what numbers you pass. In this case, I'm passing through 1, then 2, then 3 as I'm closing my fingers. 1, 2, 3, 1, 2, 3, 1, 2, 3. Forget about 4. You've already dealt with 4. Now you only have to worry about 1, 2, and 3. So you have 1, 2, 3, 1, 2, 3, 1, 2, 3. And if you go in the natural order of counting, for example, 1, 2, 3, then you have a chiral center that's R. Okay, now let's look at this example. Here, our hydrogen atom is pointing out of the page, so we stick it out. In this case, you curl your fingers this way because you can't curl it that way, all right? So we're going to go, so remember, forget about 4. We already dealt with 4. Now we're going to worry about 1, 2, and 3, and what order we go in. So we go 1, 3, this is 3, 2, 1, 3, 2, 1, 3, 2, 1, 3, 2, 1, 3, 2, 1, 3, 2. That is not the natural order of counting. It's out of order. You don't count you naturally don't count numbers 1, 2, 3, 4, 5, 6. You naturally count numbers 1, 2, 3, 4, 5, 6. You don't go 1, 3, 2, 5, 6, 8, 9, 7. Okay, you don't go like that. Okay, so when the order of counting is not natural, for when it's like 1, 3, 2 in this case, then you have a chiral center that is S. You have an S chiral center. Okay, so therefore these two are enantiomers because one chiral center is R and the second chiral center is S, and from this you can conclude that both protons are enantiotopic. All right, so just to cover enantiomers in more specific detail, let's say you have chiral centers that are 1R, 2R, and 3S. In order to have a proper enantiomer, it has to be the same number but opposite letter. So for example, if you have 1R here, this should be 1S. If you have 2R here, it should be 2S. If you have 3S here, it should be 3R. Okay, same number, opposite letters. Okay, switch between R and S. So another example, 5R7S, if you want to find its enantiomer, it better be 5S7R. Now, what about this case? You have 1R, 3S, 4S, 10S, 19R. You're not going to deal with a compound this complicated, but it's just like a basic example. All right, so you have 1R, 1S, right? Opposite letters. 3S, 3R, opposite letters. 4S, 4R, opposite letters. 10S, 10S. Whoa, not opposite letters. This is S, this is S. That's not right. So when you have letters that are the same between two different compounds, they're no longer enantiomers. They gotta be the opposite in all cases. So therefore, these two compounds would not be enantiomers. They would be diastereomers. That's what they're called. And this brings us into the third and final substitution test. The substitution test for diastereotopicity. So you have your original compound, you do one substitution, you do the second substitution, right? And you have two new compounds, and in this case, they should not be enantiomers, they should be diastereomers, okay? So, let's start with this more involved example, okay? Alright, so, we're going to find out if these two protons are diastereotopic, and we're also going to find out if these two protons are diastereotopic. So it's two examples in one, basically. So first of all, we're going to focus with proton, okay, so we have here proton pair A, and here we have proton pair B. So we're going to replace with iodine, but we're going to focus on proton pair A first, okay? So if you replace this hydrogen with iodine, you get this. If you replace this hydrogen with iodine, you get this, okay? You got these two different compounds. So we're not dealing with these right now. Forget about these. We're only focusing on these. Focus on one proton pair at a time, okay? So now we have to find the chiral centers, all right? So here we have one substituent, second substituent, third substituent, four substituents. They're all four different things, right? Four different things, four different substituents. This center is chiral. But this center is also chiral because you have your methyl group here, CH3. It's invisible, but it's there. You have this mumbo jumbo. You have a hydrogen here, and you have a bromine here. Four different things. This is also a center that's chiral. This is achiral because you got two hydrogen atoms that are the exact same thing. And here we have the two chiral centers, just like in this compound right here, okay? So doing the priority rules again, this has the highest atomic number 1, lowest atomic number 4. Next is this entire mumbo jumbo is 2 because you have carbon, and then you have all this mumbo jumbo, all this stuff here, and this would be priority number 3 because you have carbon, but then it ends. You only have a methyl group here. You have carbon and 3 hydrogens. Here, you have carbon and all this stuff here. So this entire group, this entire substituent, has a higher priority number than this one, okay? So this is 1, this is 2, this is 3, this is 4. Hydrogen has the lowest priority. Put your thumb into the page. You go 1, 2, 3. 1 to 2 to 3, 1, 2, 3. So this is R, and now we're going to deal with this chiral center. You put your fingers into the board again for H, and then you curl your fingers. So it goes from 1, this would be 2, and this would be 3, right? This is 1, this is 2, this is 3. This is kind of hard to see, but this right here is number 2 because you have carbon right here, our center. Here you have carbon, and here you have carbon, right? But here you have bromine, here you have chlorine, and then you have another carbon here. So this has the higher priority, okay? Higher atomic numbers here than this one. So this is 2, this is 3. So you curl your fingers like that, 1, 2, 3, 1, 2, 3. This is also R. So you have 2R, 3R. And then if you do a similar analogy for this one, finding the chiral centers again, I'll leave that to you as practice, you would find out that this is still R, but now that you have these two flipped because of the substitution, this would be 3s. So these two are diastereomers because you got 2r, 2r. These two are the same. They shouldn't be. If you want them to be enantiomers, it would be, for example, 2r and 2s. But here you have the same thing. You have 2r, 2r. So as a result, these two can't be enantiomers. They got to be diastereomers, okay? Based on the previous basic examples I gave you, got to be diastereomers because you got the exact same letter here in the exact same atomic position. Now we're going to focus on Proton Kerby. You work it out in a similar fashion, all right? You do the priority rules again. Chiral center here, chiral center here, chiral center here, chiral center here. Again, this is 2r, this is 2r, okay? This would be 4r, this would be 4s because, okay, so iodine, highest priority, followed by chlorine, followed by all this carbon mumbo jumbo here, followed by hydrogen. So put your finger into the page, 1, 2, 3. Curl like that. You're curling like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. This is R, okay? Natural order. Here, you have hydrogen pointing out. Curl your fingers. You start at 1, you go to 3 this time, and then you go to 2 here. 1, 3, 2, 1, 3, 2. Not the natural order of counting. This chiral center is S, so you would end up with 2R, 4S. So this proton, these two protons right here in Proton Kerby, they are also diastereotopic, okay? And we have these conclusions here. So the question is, how many different protons do we have? Well, these two protons are different, they're diastereotopic. These two protons are also different, they're also diastereotopic. So you have 4 different protons. So you might be tempted to say, oh, we got 4 different protons total. That's not true. My question is, how many different protons do you have in your entire compound? Here we got 4 different types of protons here. What about this one? This one's also different from all these, right? So this would be 5, and then finally you have your methyl group, all right? You got your CH3 methyl group that's there. Now these protons are, basically speaking, they are not diastereotopic. They are not diastereotopic. They are chemically equivalent. You can do the substitution test to figure that out. So you have 1, 2, 3, 4, 5, 6 different types of protons, okay? And I'm also going to be making another video where we have more examples of homotopic versus diastereotopic versus enantiotopic. But in the meantime, I hope these examples helped, and thank you for watching.